So our next topic in lecture 8 is tropical surfaces, and we're going to focus on surfaces in 3 space only in this lecture. So a classical surface X is the variety defined by one polynomial. We're going to look in ambient 3 space, but we take the ambient 3 space to be the 3-dimensional torus over a field K with valuation. So F is a Laurent polynomial. That's a Laurent polynomial in 3 variables x, y, and z. And v of f equals x is the classical variety, and by this we mean, this is what we mean by a surface. Now then, the associated tropical surface the tropicalization of x, so this is a non-homogeneous polynomial, so it lives in R3, and we know that this is a pure 2-dimensional balanced polyhedral complex. And we also know how to find it, right? It's dual to a regular subdivision of the Newton polytope. So here in this lecture, f is a polynomial, Laurent polynomial in 3 variables. So the Newton polytope lives in 3 space, so it'd be typically a 3-dimensional convex polytope. Now I'm going to say the tropical surface is said to be smooth or tropically smooth. So the tropical surface is said to be smooth if this meaning the regular subdivision of the Newton polytope, is a unimodular triangulation. And a unimodular triangulation is a triangulation, so each maximal cell is a tetrahedron, and unimodular means that these tetrahedra have volume 1 over 6, or lattice volume 1. They're the smallest volume lattice tetrahedra. So you're chopping your 3-dimensional polytope into such unimodular tetrahedra, and this we call a unimodular triangulation. And if that is the case, we're going to say the tropical surface is smooth. Now, why should this be called smooth? Well, this requires a little bit of justification, but this is given in the book. So this is justified by proposition 451. In fact, this proposition is formulated in any dimension for hypersurface in any n-dimensional space. And it says that if you have any classical hypersurface whose corresponding tropical variety satisfies this, whose tropical hypersurface is tropically smooth, then the classical variety is smooth. So tropically smooth hypersurfaces are those with the property that every classical hypersurface in the fiber is smooth. Every is a big set. Remember that fibers of tropicalization tend to be big sets, so this set they're all smooth. If you have a tropical surface that's not smooth, there's still many preimages that are smooth, but there exist some preimages that are not smooth. Okay, classically smooth. So this is proposition 451. Now what can we say about the combinatorial structure of these tropical surfaces in 3 space? Four, 5, 2, and let's, for simplicity, take a polynomial now, not a Laurent polynomial, but a polynomial of degree d that has full support. So we're going to assume that the Newton polytope is actually d times the standard tetrahedron. So f is a polynomial of degree d, and you actually have, x to the d, y to the d, z to the d, and the constant term appearing, and everything else in between. Right? So this hypothesis comes from the smoothness. So if the tropical surface S, so the tropicalization of the classical surface, is smooth in the sense of this definition, then it, namely the surface, has the following characteristics. It has d cubed vertices. It has 2 times d squared times d minus 1 edges. So by an edge we mean a bounded one-dimensional cell. It has 4 d squared rays, unbounded one-dimensional cells. It has 1/6 d times d minus 1 times 7d minus 11 bounded 2 cells. Let me write this on the next line. There's this many bounded 2 cells. And finally, has 6 times d squared unbounded 2 cells. Okay, so bounded 2 cells are polygons, convex polygons, and these unbounded cells are unbounded 2-dimensional convex polyhedra. Okay. Now, this is an integer. Okay, so if d is an integer, then 1/6 times d minus 1 times 7d minus 11 is an integer. That's a non-negative integer, so everything is a non-negative integer. So we know how many vertices, how many edges, how many rays, how many polygons, and how many unbounded polygons. The Euler characteristic, therefore, can be read off. Let's do that. So this is the usual, not the reduced Euler characteristic, but just the Euler characteristic of this polyhedral surface is given by the number of vertices minus the bounded edges plus the bounded cells. Right? So the unbounded stuff can be contracted in. The unbounded stuff does not contribute to the Euler characteristic. So the Euler characteristic is d cubed minus this number, 2d squared times d minus 1, plus this number, the bounded cells. So I take the alternating sum, and if you work this all out, this becomes 1/6 times d minus 1 times d minus 2 times d minus 3 plus 1. Okay, so d minus 1 choose 3 plus 1, the Euler characteristic. Okay, very good. So this is the theorem. Now this Euler characteristic is also the classical Euler characteristic. Right? I think there will be a lecture next week, on maybe following week, on the topology of complex surfaces. This is actually the Euler characteristic in the classical sense, and it's reminiscent of the degree genus formula for curves in the plane. Right? So for curves in the plane, we had d minus 1 choose 2. For surfaces in 3 space, we have d minus 1 choose 3, and so on. And we can see that purely polyhedrally by taking the alternating sum of the face numbers of bounded faces. So this is how a smooth surface looks like. So let's discuss this in some scenarios. Maybe we'll keep this up and we'll do it here so we do not erase these numbers. So let's talk about quadrics first. So this is d equals 2. Quadratic surfaces. Well, so let's plug in, right? So on a quadratic surface, there are 8 vertices. See, the number of vertices is the normalized volume, right? Because the vertices of the surface are dual to the tetrahedra. So we have 8 yellow tetrahedra, and dually we have 8 red vertices in the tropical surface, the object that the architects among you like, right? So we're now building this surface. So first the 8 vertices. That's bounded, the 8 bounded edges. So this number is 8. The number of rays is 16, 4 times d squared, 16 rays. And then in terms of two-dimensional faces, there's 1 bounded face and 24 unbounded two faces, right? So this interesting number here turns out to be 1 if you plug in d equals 2. And so on a quadratic surface, there's exactly 1 red bounded polygon. As always, on a smooth surface, there's 1 red bounded polygon. So the Euler characteristic is 1, right? So it's 8 minus 8 plus 1, and that's correct, right? That's a rational surface. So again, this is the Euler characteristic, not the reduced Euler characteristic. It's a quadratic surface in 3 space. Now these these unique polygons are kind of interesting. They can come in various shapes. They can be triangles, quadrilaterals, and so on, and all the way to octagons. So if you go over the combinatorial types, these are the things you see. So there are the various combinatorial types, and there are 192 distinct combinatorial types of smooth quadratic surfaces in 3 space. And as you go over these types, you can see polygons of the 3, 4, 5, 6, 7, 8 vertices for the unique bounded two-dimensional cell. Up to symmetry, there are fewer, so they come in 14 symmetry classes. Up to relabeling the coordinates, and that's the content of proposition 454, right? So there are 192 unimodular regular triangulations and 14 symmetry classes. So the way you compute these things is by calculating the secondary polytope. That's a systematic way of finding all triangulations. Then among these you identify the unimodular triangulations. So these are, and in this case they're actually listed. Okay. Now for quadrics in the book. So for quadrics, every point in the bounded 2 cell has a nice property. So it's proved that every point in the unique bounded 2 cell lies in precisely 2 tropical lines inside the surface, that lie on the surface, inside the quadric. Okay, so this is mirrors the very classical fact that a quadratic surface, so if you have a quadratic surface like this, then there are 2 rulings, right? There are 2 families of lines on a quadratic surface. So on the real picture, you can sort of visualize them. One ruling goes this way, and the other ruling, goes the other way. So there's 2 one-dimensional families of lines on a quadratic surface, and through every point on a smooth quadratic surface, there are exactly 2 lines, right? So how do you see this? Right? Suppose you have a quadratic surface, and you're on a point. Look at the unique tangent plane. So that tangent plane intersects the quadric in a quadratic curve, right? You have a quadratic surface, you intersect it with the plane, you get a quadratic curve. But since the plane is tangent, the quadratic curve will be singular. That's the definition of tangent, right? But a singular quadric in a plane is 2 lines. The only way a quadratic curve in the plane can be singular if it's 2 lines, right? So therefore, I have these 2 lines, and then you infer that these lines, so by construction, these two lines are on the surface, right? Because they're the intersection of the tangent plane with the surface. So classically, for every point, there are two lines. Entropically, this is true on the bounded 2 cell, but it's no longer true outside the bounded 2 cell. Now, another family that's very interesting are so-called quartics. Let's talk about quartic surfaces for a moment. So quartic means d is equal to 4. So let's plug in d equals 4. So the number of vertices is 64. Now that's the normalized volume of a standard tetrahedron scaled by a factor of 4. So there's 64 vertices. There are 96 bounded edges. There are 64, these are these numbers, 64 rays. There are 34 bounded two-dimensional cells, and there are 96 two-dimensional unbounded cells. Okay? So what's the Euler characteristic? Well, 64 minus 96 plus 34 makes 2. Okay? So these are no longer rational surfaces, so we up the Euler characteristic from 1 to 2. Now, these degree 4 surfaces are important examples of what called case 3 surfaces. It's an example instance of a K3 surface. Now, the polytope has the property that there is exactly one interior lattice point in the Newton polytope. In 4 times the standard tetrahedron. So the Newton polytope has exactly one interior lattice point in the interior. So a little exercise, right? You start with the standard tetrahedron. You blow it up by a factor of 4. On each facet, you now have 10 lattice points. But in the interior, there's exactly one. Exactly one lattice point. So in that sense, it behaves like a cubic curve in the plane. Okay? So well, the polytopes or hypersurfaces that have this property are sometimes called Calabi-Yau. So this is a Calabi-Yau surface. Elliptic curve is a Calabi-Yau one-fold. 2 points on a line is a Calabi-Yau zero-fold, but the universe is made up, from one dimension higher, Calabi-Yau three-folds. Okay, so this is one interior lattice point. Well, if there's one interior lattice point, what does that mean? Well, that means in the tropical surface there is a distinguished polytope, and these are called K3 polytopes. So the tropical surface will have a unique two-dimensional cycle, right? So you have this yellow triangulation, this yellow unimodular triangulation into 64 unit tetrahedra. This yellow unimodular triangulation, think about the architects, has one interior lattice point. So dually in the red picture, this lattice point will be, corresponding to a polytope, a red polytope that's hollowed out. Just like in the elliptic curve case, we had a unique cycle. Now we have a unique polytope. And this is a very interesting family of three-dimensional polytopes. They're called K3 polytopes. Okay, here's a theorem. 458. That says things get a bit more interesting in tropical geometry. Here is where tropical geometry diverges to some extent from classical geometry. So suppose d is greater or equal to, and you look at the Newton tetrahedron here. So the tetrahedron d times delta 3 admits regular unimodular triangulations. More than one. With the property such that all corresponding smooth surfaces, corresponding smooth tropical surfaces contain infinitely many lines. Many tropical lines. So let's discuss this for d equals 4. So in the classical setting, for a quartic surface, a typical quartic surface in 3 space contains no lines whatsoever. Right? So there will be no line on a quartic surface. But here there is an entire family. Right? So there are smooth tropical surfaces of degree 4 that contain infinitely many lines. And in fact, in every degree, this can be done. So this is very much counterintuitive. This is the analogous statement in classical geometry would be very false. Right? But, okay, that's theorem 458. Now in the book we are presenting an explicit construction of this. So this is example 4, 5, 10. We're listing an explicit triangulation that has this property for d equals 3. And this was found in the dissertation of Magnus Vigeland from Norway. So with that in mind, let's talk a little bit about cubics. Cubics are always interesting. So that's surfaces of degree d equals 3. So let's run our statistics. So here the number of vertices is 27, d cubed is 27, the number of edges is 36, the rays is 36, polygons is 10, and unbounded are 54. Okay? So let's check the Euler characteristic. 27 minus 36 plus 10 makes 1. So the cubic surface, just like the quadratic surface, is a rational surface, so the Euler characteristic is 1. And these are special cases, rational surfaces called Del Pezzo surfaces. So this is a cubic surface is an example of a Del Pezzo surface. So in the abstract theory, these are called K3 surfaces, and these are called Del Pezzo surfaces. Now there is a very important fact about cubic surfaces, the classical theorem. So classically, on a smooth cubic surface over an algebraically closed field, there are always 27 straight lines. Every smooth surface, say over the complex numbers, contains exactly 27 distinct straight lines. But here the Vigeland example, there's infinitely many lines. There's an explicit, tropically smooth surface that has infinitely many tropical lines. So tropical line, looks like this. Okay? So the question is, what's going on here? So this example, this behavior of cubic surfaces and sort of the mismatch of the 27 lines versus infinitely many lines has puzzled people for a while. Now there has been significant progress on this, but we do not really fully understand it. So the ultimate understanding, I think, is still out there, and I think it's an important topic still to work on to sensitize you a little bit to what's involved. Let me give you an exercise. Let me state an exercise from the book. So this is exercise number 30 from chapter 4. And it asks the following: find a classical polynomial, so find a cubic polynomial f, but we'd like you to find it with rational coefficients in x, y, z, such that the classical surface, now we take the closure in P3, so let's take an inhomogeneous polynomial, homogenize it, and let's look at the corresponding projective surface in P3 such that the following property, that this classical surface is smooth. So I want my surface to be smooth, and its 27 lines should be all defined over Q. And that's the first part of the exercise. Okay. So I mean that each straight line is given by two inhomogeneous linear equations with rational coefficients. Okay? I want the lines also to be defined over Q. And once you have such an example, I'd like you to compute and draw. Compute and draw the p-adic tropicalizations for some primes p. Well, you can draw the surface, but in particular, on that surface, I want you to draw the 27 lines. Okay, so for p equals 2, 3, 5, maybe take the first 3 primes. Right? So you're given the surface, and it's smooth over the rationals. Then you look at a prime like 3. Okay? Then there's a 3-adic tropicalization. That's going to be a tropical surface. This may or may not be smooth. It would be nice if it were smooth. Then, it has these characteristics, but I may not even ask that. But what I do want you to draw is the lines. Right? There are 27 classical lines, and they are defined over Q. Right? So there's no issue about what the valuations are. This is a classical line defined over Q, and so there's no issue of extending the valuation. And I want you to explore that. Okay? That's the task. Now, if you've never thought about cubic surfaces, this is quite hard, right? So the naive approach, if you've never done this, you pick maybe your f at random with rational coefficients. Then you set up a system of polynomial equations that has 27 solutions, and those 27 solutions will not be defined over Q. And you do it again. You do it again. You do 10,000 examples, and it will essentially never be the case by a random choice that your lines are defined over Q. So any kind of random construction will bitterly fail. Okay? But the way you do this is to have a little bit of insight. Right? So the way this classical fact is proved and the way cubic surfaces are constructed in algebraic geometry is by blowing up the plane at 6 points. Let me explain this, right? Because I think it's good to know this. So you pick 6 points in the plane with rational coordinates, in the projective plane with rational coordinates. Okay? Then you look, and let's say they're in general position. No 3 on a line, no 6 on a, not all on a conic. Okay? Then you look at the space of cubic polynomials that vanish at those 6 points. And that's a 4-dimensional vector space. So let's call these cubics Alice, Bob, Charlie, and Dora. Right? That's a basis of that space of cubics. Well, there's a 10-dimensional space of cubics. They vanish at 6 points, so there's a 4-dimensional solution space. Okay? Now you take Alice, Bob, Charlie, and Dora, and you map the plane into 3 space. Right? You just use them as coordinates for a map from P2 to P3. Well, that map is well defined everywhere except at the 6 points, right? Because they vanish at those 6 points. But the closure of the image of this map is the cubic surface. Okay? So I promise the closure of the image is a cubic surface, and in fact every cubic surface comes this way. But since you started with 6 points in the plane whose coordinates are rational, all the 27 lines afterwards will be rational. Right? So the way the 27 lines arise, I mean, this is a beautiful story, right? So there will be 15 lines spanned by pairs of points in the plane. They become lines in the image. There will be 6 conics passing through 5 of the 6 points. They become lines in the image. And then there are the 6 images, so the holes that you fill in, the exceptional divisor over the 6 points, and that's the 27. Okay? So what I just told you is that 15 plus 6 plus 6 makes 27. Anyway, so the tropical cubic surface and the lines is still an interesting area of research. Now let's shift gears. Let's now look at 2 surfaces, and let's intersect them. What can we say if we take not just one surface in 3 space, but now we take 2 surfaces in 3 space, and let's intersect them. So I take two of these, say smooth surfaces, and I intersect them. We have the following result about this intersection. So this is proposition 4,620. So let's start with classical polynomials f and g in x, y, z, coefficients in a field with valuation. And let's say these classical polynomials have degrees d and e. And again, the equations are dense in the sense that the Newton polytopes are as big as possible. So with Newton polytopes, d times the standard tetrahedron, respectively e times the standard tetrahedron. Now let's look at the tropicalization of the classical curve. So I'm going to assume that the tropical curve, which I'll denote by sigma, so this is the tropicalization of the classical curve that I get by intersecting the two surfaces. So the variety of f and g together should be a curve, and we're looking at the tropicalization of this curve. And I'm going to assume that this is now smooth, tropically smooth. Okay? And this I did not yet define. Okay? I will define it in a moment, but there's a combinatorial condition reminiscent of the unimodular triangulation condition that says that this graph, that this tropical curve is smooth, and I'll come back to this. Under this hypothesis, the tropical curve, sigma, has the following characteristics. It has d squared e plus d e squared vertices. It has 3/2 times d squared e plus d e squared minus 2 d times e edges. And finally, so these are bounded one cells, and finally there's 4 times dE rays. Right? So this is one dimensional, so just vertices, bounded edges, and rays. And those are the numbers. Now from this, we can calculate the genus of this tropical curve. So the genus of the tropical curve, well, again, you can forget about the unbounded rays. They do not contribute, right? So the genus of a graph is the number of edges minus the number of vertices plus 1. Right? This is the number of independent cycles in the graph. That's the genus. So this is E minus V plus 1. So it's this number here. Maybe color code this a little bit. So the number of edges, the red number, minus the number of vertices. That's this number plus 1. That's the genus. Now, how do you prove this? So the proof as well as the definition of smooth, so proof idea, is that you triangulate a certain polytope. But what you triangulate is the so-called Cayley polytope. So the Cayley polytope is made up of the two given polytopes. So the Cayley polytope of the first tetrahedron and the second tetrahedron. So that's a certain polytope that lives in 4-dimensional space. So what's the Cayley polytope? So suppose you have two polytopes in the same space, let's say 3 space, and you take one copy of this 3 space, and then you take another copy parallel to it up in 4 space. You place your first polytope in this space, your second polytope up there, and you take the convex hull. Right? You simply take your 2 polytopes, that makes a 4-dimensional polytope. Right? So this is the Cayley polytope. So this you can do for any pair of polytopes in any space. In fact, you can do this for any finite collection of polytopes. You sort of make a new polytope out of a collection of polytopes. And then the correct definition of smooth is that this induced subdivision of the Cayley polytope should be a unimodular regular triangulation. Well, why does this make sense? Well, the Cayley polytope, the vertices of the Cayley polytope are the vertices of the first polytope at the level 0 and the vertices of the second polytope at level 1, but those are in bijection with the terms of f and g. Right? So the valuations of the coefficients of f give heights of the first bunch of vertices. The valuations of the coefficients of g give you the heights for the second collection of vertices. So then now you have an induced regular triangulation as before, and this regular triangulation we now want to be unimodular, and that's our hypothesis. And then by analyzing this triangulation, we get the genus. So this is a mixed situation. Okay, let's look at some examples. It's instructive to see some examples. So for example, if I have two quadratic surfaces, d equals e equals 2, right? Then the numbers are 16, 16, 16. It turns out that all three numbers happen to be 16. So these are intersections of two quadratic surfaces in 3 space. These are elliptic curves. And a nice question is, how many types are there? How many combinatorial types are there? You can see the genus is 1. 16 minus 16 plus 1. So there's a unique cycle. Right? There's a unique cycle in this curve. So there's an elliptic curve. It has a group structure. This is a nice case, right? So some of us are interested in pencils of quadrics and LSSMs, linear spaces of symmetric matrices. So here we're speaking about a 2-dimensional linear space of 4x4 symmetric matrices, and we get these types, and this is a nice combinatorial problem to look at this tropically. The next example up would be maybe d equals 2, e equals 3. So I'm intersecting a quadratic surface with a cubic surface. So this makes a surface of a curve of degree 6. So then our numbers are 30, 33, and 24. So now I have a graph with 30 vertices. That's the the yellow number, 33 for the red number, and then 24 rays. So now the genus is 4. You can see it's a genus 4 curve, and these are called space sextics. And these happen to be classically, they are canonical curves of genus 4. They have very rich geometry, some of which we see in their shadow under tropicalization. So if you intersect two surfaces in 3 space, you get these kind of curves. Now what happens if you intersect 3 surfaces? So now let's intersect 3 surfaces. Well, one thing you could maybe think about is you count the points via Bézout, right? I mean, now, classically, it's not so interesting anymore, right? You have 3 surfaces, maybe of degree d, e, and f. Then you expect d times e times f points, if these are dense surfaces. But even there, you can ask interesting questions. So here's a question, right? So should we count via Bézout? Well, let's count via Bézout just for now. So what happens, for example, if you intersect 3 quadratic surfaces? We get 8 points. But which 8 points do you get? So here's a question. Which 8 points in R3 are intersections of 3 tropical quadrics. Right? So now we take a net of quadrics, an LSSM, a 3-dimensional linear space of 4 by 4 symmetric matrices, and associated to this will be 8 points classically. But what about tropically? What do you get? Right? So if you take 3 tropical quadratic surfaces, the ones we discussed, you intersect them, which 8 tuples of points can you get? This, I think, is an open question, actually, and it's a good question in my view, because the classical answer are the so-called Cayley octets. So classically, in classical geometry, not every 8 tuple of points is the intersection of 3 quadratic surfaces. There's a very interesting codimension 3 condition. Very interesting codimension 3 condition. Here's one way to state the condition. You have 8 points in projective 3 space. You can write them as the columns of a 4 by 8 matrix. So that's a rank 4 matroid on 8 elements. Look at the matroid dual. That's a rank 4 matroid on 8 elements. To be a Cayley octet means that these are the same matroid up to relabeling. Right? So Cayley octets correspond to matroid self-dual configurations of 8 points in 3 space. That's a codimension 3 condition. This kind of matroid duality is actually Riemann-Roch. This is the Riemann-Roch theorem on the associated genus 5 curve, of which this is a hyperplane section. Right? So if you have a genus 5 curve, the canonical model is the intersection of 3 hypersurfaces in P4, the genus 8 curve. The canonical divisor is the Cayley octet. Right? The canonical divisor is the intersection with the hyperplane. This is a canonical divisor in genus 5. It satisfies Riemann-Roch, and Riemann-Roch here is combinatorially matroid self-duality. Okay, so there's some geometry in the background. So I think this is a good question, probably unanswered tropically. Now, when tropically geometry in this form started, now nearly 2 decades ago, you could take any question, you could ask it tropically, and often you got something very interesting. So 10, 15 years ago, there were lots and lots of low-hanging fruits because it was a new subject. In the meantime, a substantial body of work has emerged, and there are far, far fewer. You have to climb up higher to find the fruit, but there's still lots of very, very good questions. So this is just an example of the kind of question that you can ask. But let's go back to the other question. Should we count intersections points by Bézout's theorem? Is Bézout's theorem a good theorem? No. Right? It is a good theorem, but of course it's important to know Bézout's theorem in its classical form. But if you want to count the solution set to a square system of polynomial equations, Bézout's theorem in practice, in applications, is surprisingly useless. And the reason is that you very rarely in practice encounter dense sets of polynomials. In my view, a better theorem is Bernstein's theorem. Let me end by stating Bernstein's theorem. So this is also towards the end in chapter 4, so it comes in 2 versions, theorem 468, and then perhaps a little easier to digest 4614. And it says the following: the number of intersection points is the so-called mixed volume of the 3 Newton polytopes, or in general n, if you're in n space. So if you have, let's call these Newton polytopes maybe P, Q, and R. So if you have 3 surfaces in 3 space, maybe the Newton polytopes are not the standard tetrahedron. Maybe they're not all scaled. Maybe there's some other Newton polytopes. Then you get a more interesting answer. It's the so-called mixed volume. And let me define the mixed volume for you. What you do is you take the Minkowski sum. It's It's defined by the following inclusion-exclusion formula. So you take the sum of P, Q, and R, and you calculate its volume, and this is the classical volume. So this might turn out to be 1 over 6 or something over 6. And then you subtract the volume of P plus Q minus the volume of P plus R minus the volume of Q plus R. But then, as always in inclusion-exclusion, you have to add something in, namely the sum of the volumes. Okay? So these are the classical volumes in 3 space. So these are rational. These could be rational numbers with denominator 6th. So the miracle is that this number I wrote down is an integer, and in fact it's non-negative, and in fact it counts the number of solutions. Okay? Now if P and Q are standard tetrahedra, you recover Bézout's theorem. So this is a generalization of Bézout's theorem, and it is a more useful count. So this holds both tropically and classically. And in fact, my favorite proof of the classical fact is the tropical proof. Let me end with an observation that's important, namely that generic complete intersections, even in the constant coefficient case, are always tropical bases. That's a very useful fact, and that's theorem 4, 6, 18, the precise statement. So this is kind of a useful fact. So if you take sort of general polynomials somehow, and this requires definition, so I'm not going to define this right now, but in the appropriate notion of genericity, we have 3 equations and 3 variables. If the coefficients are generic in the sense of this theorem, they will automatically be a tropical basis. Now this is useful because it's a scenario where you are very far from a Gröbner basis, but you do have a tropical basis. And then often in numerical methods, one numerical method for classical root finding is you first find the tropical roots, counted here by the mixed volume, and then you homotope them to the classical roots. But that would be another story. So this is it for chapter 4. So next week we'll have chapter 5 and chapter 6. We will focus on chapter 5. We'll talk a little bit about convexity, tropical convexity. And then for chapter 6 next Friday, you might have to buckle your seatbelt. It's called toric connections. So we'll go on more into algebraic geometry. Thanks for your attention, and I welcome your questions. I'm sorry, how? How likely is it to be tropically smooth? Okay, now that of course depends how you put the measure. Okay, so that's a very good question. So the question is, how likely is it for a tropical surface to be smooth? So let's say we purely work in tropical space only, right? So we're picking a tropical polynomial, and we pick the coefficients somehow at random, right? So there's a structure called the secondary fan. So this is a partition of the space of coefficients into finitely many cones, and if your vector, the coefficient vector you chose, lies in one of these cones, then you have a particular tropical, surface or particular triangulation. So out of this region, there will be some subpart, some subcollection of cones that will be the unimodular part. So maybe these yellow cones are the ones where the triangulations are unimodular, and everywhere else the triangulations are not unimodular, right? So you could ask what fraction of these cones is yellow over all cones, or what's the spherical volume? What's the ratio in spherical volume? That's one question. I think that's a good question. I think there's been some studies, but not much, actually. I think, again, that's a very good direction to study. We studied this for cubic surfaces. There are lots of yellow cones. There are, I think, 1.4 million yellow cones alone and many more white cones. So this becomes not so easy to enumerate, but it's a good question. I think an even better question is the following. Upstairs, over this whole situation, right, this is tropical space, coefficient space, there's classical polynomials. There's classical polynomials. And suppose you have a measure on classical polynomials, say over some valued field, right? Give yourself a measure on, vectors of p-adic coefficients. Let's pretend we have a good measure. Then what's the induced measure? What's the likelihood to land here? And I claim intuitively it's very, very low. If you have reasonable measures up here, first of all, remember the fibers are very, very big, right? The fibers are these analytic domains that are Zariski dense, right? And so the measure really messes things up quite a bit. So I think it would be very, very interesting to understand this better from the point of view of measure theory and integral geometry on p-adic spaces. Having said that, there's a recent emerging literature on p-adic integral differential geometry and p-adic random algebraic geometry, work of Antonio Lerario and actually people who were here, Avi Kulkarni. So I think this would be a very interesting direction to pursue. Other questions?
So I think I missed the sketch of this proof, but you essentially want to find the simultaneous lift of your evaluation map, right? Is that what you're...
Well, I cheated a little bit. So when I wrote proof, I'm hiding two things. Part of this is definition. I should have said definition, slash proof. So first of all, the definition of smooth is that you form this polytope, and it's smooth if the subdivision is in a modular triangulation. That's the definition part. Then the proof part is you want to derive this red and green number and yellow number by analyzing the combinatorics of triangulations of such a four-dimensional polytope. That's the proof part. You are thinking about lifting to a classical space. That's also true. So under this definition of smooth, every classical curve that lives over such a curve will be classically smooth. So that property is preserved. So this says it's the correct definition. So here we're saying we have a justification, right, in the surface case, and this justification is also valid in this case.
Yes, so I mean, then the fact that the curve has this polytope, so then you have these two tropical surfaces, and then you want to find the intersection of those. This is how you're describing it. But can you say a few words about how to justify this relation? Why is this the
right polytope? Yeah, so it turns out, so why is this the right polytope? Yeah, I should maybe, let me say a word about this. Let me try, okay? So suppose you have two polygons in the plane. Here's a polygon, and here is another polygon, right? But now let me form their Cayley polytope. So this means the yellow polygon is at height 0, and the red polygon is at height 1. Right? So now I take the convex hull, and so there will be some kind of three-dimensional polytope emerging. Right? You could imagine, now there's some kind of three-dimensional polytope that has the red polygon at the top, and then the yellow polygon at the bottom. And this is a three-dimensional polytope. And now you want to study triangulations of this. Right? So now also imagine this object is triangulated. Right? Now, let's do the following thing. Let's look at what happens at height a half. Okay, so let's slice this polytope and see what happens, at height a half. Right? So now you're going to see some green polygon, right? Now this green polygon up to a factor of 2 is the Minkowski sum of the red polygon and the yellow polygon. Okay? Now what happens to this green polygon? Well, it's subdivided, right? The big three-dimensional thing is divided into tetrahedra. Every tetrahedron meets the green polygon either in a red triangle or in a yellow triangle, or in a bichromatic parallelogram. Well, the mixed area, the number of solutions to this system of two polynomial equations in two variables, is the area of P plus Q minus the area of P minus the area of Q. It's the total area minus the yellow triangle area minus the red triangle area, and so this counts correctly. So what I'm trying to say is the Cayley polytope, if you slice in the middle, knows the intersection theory. It knows about Bernstein's theorem. So now you up this by one dimension, right? So here I spoke about counting number of points, but this analogous justification works here. Now points become a curve. So the two Cayley polytopes, so we have this Cayley polytope in 4 space, but if you slice it right in the middle, then you get the Minkowski sum. But this Minkowski sum in the presence of this triangulation comes with what's called a mixed subdivision. So there's a whole theory of mixed subdivisions and mixed fiber polytopes and so on and so forth. Okay, other questions? Yes.
How much complicated is actually like computing the mixed volume?
Okay, so the question was, how complicated is it to compute the mixed volume? Well, it turns out this formula is not an easy formula to evaluate, right? So this is not a good algorithm to compute it. But what I just said 60 seconds ago is actually a good algorithm, right? So the good algorithm is you compute a so-called mixed subdivision. This is the subdivision induced by a triangulation of the Cayley polytopes. You need to do only one time a triangulation. And you look at the various cells and you just take, add up the volumes of the most mixed cells. So that's the best algorithm. So this is quite fast. So this you can do up to dimension 10, 12 quite fast. And it's the first step in something called polyhedral homotopy. So in numerical algebraic geometry, there are a number of different methodologies for finding solutions numerically, and one methodology is to do exactly what I just said. You find the mixed volume at the beginning, but you realize the mixed volume by so-called mixed cells in such a Minkowski sum. So I would say it's not too bad. There are papers about complexity and so on. So there's a literature on how to best compute mixed volumes. Any questions in the chat box? No? Well then, if there are no further questions, I thank you for coming and I wish you a wonderful weekend.